This video was going to act as a bridge from Chapter 3 to Chapter 4. Let's remind ourselves of what Chapter 3 was about. Chapter 3 was about constant or average velocity. In other words, I have that equation for average velocity and I get a number, and it's just a number, right? That ratio, delta x to delta t, is constant for that amount of time. For example, let's suppose delta x to delta t is 2 over a time of 5 seconds. That 2, right, is a calculation based on some delta x or delta t, but that number 2 means what? It could look like this. I don't have to start down here, but it basically says that if I travel 2 meters per second for 5 seconds, how far do I go? Well, that's like what, 10 meters in 5 seconds, for example. My delta x is 10. So from here, from my starting point to my ending point, would be 10 meters, even though I started negative, right? 10 meters. But it looks, what kind of scatter plot would I get? Well, if I looked at every second where I was, maybe I started down here. 1 second later, I would have gone 2 meters. Another second later, I would have gone 2 meters. Another second later, I would have gone 10, et cetera, et cetera. So this is a 2 seconds, sorry, that should be 2 meter delta x. Right? Every 1 second delta t. And then we can what? Interpolate, right? We could say our motion is best modeled by a line. The slope of that line would be delta x over delta t, and you could do that for any pair or any position on that line, any coordinates, and as long as, and my slope would be a constant 2, no matter where, right? So let's interpolate this, and I get a slope, and that's my average velocity of 2 meters per second. I could look at that velocity because I could graph velocity. In other words, I could calculate velocity anywhere using the line, and the slope's always 2, so my velocity time graph would look like this. I'm going 2 meters per second the whole 5 seconds. First thing to note, we took a slope of a graph and we found out it had meaning. Over here, let's look at the slope, but it's kind of trivial, right? Because for that, over that delta t, whatever delta t corresponds to that average velocity, my slope is 0, so it's kind of boring. If you recall, we just got straight lines. They could be positive, they could be negative, they could be big positive, they could be big negative, but we just got it looked like a stair step, or stairs, right? Just a bunch of straight lines. So that's Chapter 3. Chapter 4. What was the main, to understand Chapter 4, to appreciate Chapter 4, let's look at the boundary constraint for Chapter 3. I'll express it mathematically, which is that this ratio of displacement for a certain amount of time is constant. That was the model of Chapter 3. So all it could tell us was average velocity. Or it was only good at modeling constant velocity because the average velocity during the 5 seconds is this constant velocity of 2 seconds. Okay. In Chapter 4, we release or we relax the boundaries. The first boundary is that this is no longer constant. But what is constant? We're going to let this ratio, the slope of this graph, we're going to make it constant. What does that mean? If delta v over delta t is non-zero, because 0 is trivial, right? But constant, then we're entertaining a different picture than this. We could have a picture that looks like this. I've got a velocity, and just to keep things simple, I'll just stay in the positive the whole time. So I might have a velocity that, let's say I start here, and instead of staying constant at 2, I'll say it increases by 2 every 5 seconds. So, and I'm picking these numbers just because they're easy, I think, if you want to make them real numbers. 1, there's my first second. 1, 2, 3, 4, 5. Why am I placing the dots this way? Because I said my delta v to delta t is constant. So delta v to delta t here, that delta v is now on the vertical, just like this graph. Delta v and delta t, rise, run, is constant. So that means the best, whoops, couldn't draw there, right? If I interpolate or if I have the information, it's actually a line. The slope might be, just as an example, maybe the slope of this line is a rise, it equates to a rise of 2 meters per second, because that's the units of my axis. So my rise is 2 meters per second, and let's say my run is 1 second. Right, so if delta V is 2 seconds, delta T every 1 second, then I now have, oops, sorry, not 2 seconds, 2 meters per second, and my change in time is 1 second. Let's say my slope is 2 meters per second for 5 seconds. Then my velocity will increase or change for a total of what? 2 meters per second for 5 seconds, 10 meters per second. Okay? So this is the new world we're entering in chapter 4. And if we have a shape like this, we notice that we had a shape like that over here, but that was position time. And then we got another graph when we took the slope. You could graph the slope of this line. It's boring but constant. It's boring because it's constant, but it still has meaning, right? We found out that if we look at the slope of this line of an xt graph, we get velocity. Well, if I have a velocity time graph and it's not boring, this one's boring. Ho-hum, the slope is 0. This one's not boring. I have a number, but it's constant. That means if I graph the slope of this line, now I get 2 meters per second for the whole 5 seconds. The question now is, what is the vertical axis? Da-da-da! Chapter 4 talks about acceleration. Acceleration is delta V over delta T, and it's the average acceleration, just like we have an average velocity of delta X over delta T. Average acceleration is delta V over delta T. Welcome to chapter 4.